Good. So without further ado, I'm going to introduce Jim Kasting, who got his undergraduate degree from Harvard and then his master's and PhD in atmospheric science from the University of Michigan. Then he spent some time at NASA Ames as a postdoc and then a scientist, and since 1988 has been the professor of geoscience and meteorology at Penn State. So, Jim.
Okay, thanks, Greg, and thanks, Adam, for inviting me. I'm delighted to get a chance to talk to you. I'm a theorist, so we've gone theorist, observer, theorist again. But I'm a slightly different type of theorist because I'm not really an astronomer. I'm in a geosciences department. I'm more of an earth scientist, earth/planetary/atmospheric scientist. And these days, we get funding from NASA for doing astrobiology. So we actually all call ourselves astrobiologists. As you already heard from Alan's talk earlier, what we're all interested eventually is looking for Earth-like planets out there, and not just the planets themselves, but for evidence of life. So that's what I'm going to talk about. And actually, Deborah and Alan have set me up really well. There'll be just a little bit of overlap between my talk and Alan's, but I thoughtfully figured out what they were likely to tell you, and so I think I've pretty much avoided too much duplication. Let me start out here with a slide that I got from Mike DeVirian, who's part of the program office, the NASA Exoplanet Program Office at JPL. And he was giving a talk. This was shortly after funds for some of these planet-finding missions that I'll talk about had been cut a few years ago. He was pointing out that planet finders have had a hard time of it for a long time. And back in ancient Greece, Epicurus actually wrote some articles saying that he thought there were lots of worlds out there like our own. Aristotle had argued before him that the Earth was unique. And of course, Epicurus died painfully in 269 BC, and Aristotle's views went on to dominate scientific thinking for a long time after that. Then, of course, there's Galileo, who you all are familiar with, because Galileo came along and knew that the planets went around the sun, but he was forced to recant that belief. He did, and was basically imprisoned for life. But the patron saint of planet finders is actually Giordano Bruno, who was a contemporary of Galileo's, a little bit before Galileo, actually. And he also wrote, he was a real heretic. There were lots of things about Catholic Church teachings that he didn't believe. He wrote that there are countless suns and countless Earths. It's really kind of interesting. If you go on Wikipedia, there's some really good articles on Bruno. But he, unlike Galileo, he was charged with crimes against the church, and he refused to recant, so he was burned at the stake in Campo dei Fiori, Rome. So if you ever go to Rome, that's a little plaza that's not very far from the Vatican, and you should go. This is a picture of the statue that they have there in Campo dei Fiori. And Mike DeVirian's comment when he gave this particular talk was that these days, we get our funding cut, but we don't suffer the same penalties that people did back in the past. There's lots of different opinions as to whether Earth-like planets exist, and I just want to review a couple of books, several books actually, that bear on this one way or the other. There's a whole series of books about Gaia that some of you may be familiar with. Jim Lovelock, a picture of him here, was the original author of the Gaia Hypothesis. He also co-authored a number of things with Lynn Margulis, who's a famous biologist here in the United States. These were his first two books on Gaia. Gaia, by the way, that's the goddess of Mother Earth. His theory was that life actually has a huge influence on the Earth and stabilizes its environment. This was his first book, 1979, New Look at Life on Earth. This was probably his best book in '88. If you're going to read a Lovelock book, I'd recommend that one, Ages of Gaia. He's since written, I think, 3 or 4 other books. His most recent book is Revenge of Gaia, and he's worried about global warming, and so he's really just hanging in there right now. This is just a picture of Gaia here. So Gaia is the Greek goddess of Mother Earth. And the reason I bring this in is that it's relevant to this story in some sense, because in Lovelock's view, if you didn't have life, the Earth would not be habitable. The fact that the Earth is habitable is a direct influence of life. And so that would mean that if you had an abiotic planet out there that had 1 Earth mass and was at 1 AU from its star, if it wasn't inhabited, it wouldn't be habitable. I don't actually agree with that, but that's, out there. You can find that in Lovelock's work. Sort of more directly relevant, there is this book called Rare Earth by Peter Ward and Don Brownlee. How many people here have read this book? It's a really fun book. I recommend it for reading. I don't necessarily agree with the conclusions. Peter Ward is a paleontologist at University of Washington, and Don Brownlee, some of you may recognize his name. He's a very famous astronomer, actually. He's a member of the National Academy of Sciences. He's studied the dust that comes in from outer space, and in fact, that stuff that NASA collects up in the stratosphere is sometimes called Brownlee dust because it's named after Don. In this book, Rare Earth, Peter and Don argued that Earth-like planets are reasonably rare in the universe. They're sort of the anti-Carl Sagan, and this book sold a lot of copies because they're a very different story from what Carl Sagan used to tell. In particular, they argued that complex life is rare in the universe, and by complex life, they mean animal life, which of course includes humans. And they have a variety they've got about 10 or 15 different arguments in there, a couple of which I'll talk about in this talk today, but they're very pessimistic. They think that Earth is very rare. This is Peter's. Peter writes books. He writes a book a year, whether he needs to or not. And his most recent book, I just put this up here, it's called the Medea Hypothesis. That's the opposite of Gaia. Gaia is the Greek goddess who takes care of the Earth. Medea, of course, was the Greek wife of Jason the Argonaut, Jason was suffered from infidelity, I think, and Medea punished him by killing their kids and serving them to him for dinner. So it's a terrible tragedy in Greek literature, but Peter, argues that life destabilizes the Earth's climate. He wrote this specifically because he doesn't like the Gaia hypothesis. Anyway, the latest addition to this literature is this book right here, which Alan put in a plug for his book, so I'll put in one for mine. This is my new book. That's where the title of the talk comes from, How to Find a Habitable Planet. It just came out in January. And I will say, I'm actually much more optimistic than certainly than Ward and Brownlee. And as I told you, I don't necessarily agree with Jim Lovelock either. So I'll try to make some points. I think actually related to this, I think Earth-like planets probably are pretty frequent. We heard a little bit of that from Deborah and Alan. Of course, we don't know the answer yet, but there's reasons for optimism, I think. And so I grew up. I was very influenced by the writings of Carl Sagan. In fact, what got me interested in this field was when I was in college. I read this book, Intelligent Life in the Universe, by Sagan and Shklovsky, which I was just fascinated in. That was a book that was written originally by the Russian astrophysicist Shklovsky, and Sagan got it. He thought it was interesting, and he took it, and, well, I don't think he translated it, but he took an English translation and annotated it, and, that was really caught my attention and got me interested in this whole search for extraterrestrial life. So let me give you the outline for the talk. There's the intro, which you just heard. The first part of the talk is, as I said, I do astrobiology these days, so I want to talk about what is it that makes the Earth unique, and also what is life, which is a question that one needs to talk about. And then the second part, I'll talk sort of briefly about how do we find planets, Earth-like planets around other stars. I'm going to skip over the things that Alan talked about, and go directly to direct imaging, which Alan did talk about a little bit. I'm interested, when we do get spectra of these planets, how you interpret the spectra, and so that's what I'll try to focus on in this talk. Well, let's think about the definition of life. There's lots of arguments. I've gone to Origin of Life meetings for many years, and the biologists don't entirely agree among themselves what life is. I think maybe the best definition, here's a famous biologist, Jerry Joyce at the Salk Institute, who works on Origin of Life issues. So he would define life as a self-sustained chemical system capable of undergoing Darwinian evolution. And I like that definition myself. that's the kind of definition that if you're a laboratory chemist, you like that, because Jerry actually designs experiments. He and Jack Shostak at Harvard are basically both of them trying to create life in the laboratory, not directly, but doing experiments very closely related to that. And so, that's the kind of experiment they might do in the lab. We're as astronomers, we're actually engaged in a very different type of activity. We're looking out there for evidence of life, either on planets in our own solar system, or in this case, on planets around other stars. There's no way of testing this type of theory with remote observations. So we need we need a more practical definition for life. And I'm going to be very Earth-centric here and just point out what life requires on Earth. Life on Earth is carbon-based. We know there's a unique common ancestor to all life because we all operate with RNA and DNA and have the same genetic code. All life on Earth requires liquid water during at least part of its life cycle. Even though there are some organisms, spore-forming plants, for instance, or bacteria that can go for long time periods without water, they need water to reproduce and to metabolize. So I'm going to be conservative and say we want to look for planets that have liquid water. There are biologists who would disagree with that. In particular, there's a biochemist named Steve Benner who used to be at University of Florida, and he's broken off and formed his own little company, but he was one of the authors of this National Academy report that came out a couple years ago that's sometimes called the Weird Life Report. And so Steve, the big question in our solar system is Saturn's moon Titan, which has these lakes of liquid methane. And of course, the Cassini orbiter is out there, and the Huygens probe dropped down there a few years ago. There are people who think that there could be life in a liquid like liquid methane. Steve Benner, has argued he likes to take these positions out on a limb, and so he will argue that that's not impossible. For this talk, I'm more interested in looking for life on planets around other stars, and if there is life on Titan, we certainly can't see it from Earth. We didn't see it yet from the Huygens probe. There's no way, I think, that you could tell that on a planet orbiting another star. So we're interested in water, but water can be subsurface. And of course, there's, the astrobiologists, most of astrobiology is not astronomers actually looking for life around other stars. They're looking for life in our own solar system, especially on Mars, which looks like it had water back in its past. It probably still does have water deep underground. That's very interesting for planets in our solar system because we can go there. We do go there basically every opportunity. Mars comes by the Earth about every 2 years, and NASA usually sends one or more spacecraft out there. So, I think if there is life on Mars, that it's probably deep underground, maybe 1 kilometer or so. We follow the geothermal gradient down, and there's a point at which it should warm up. You may know there's there is some evidence for methane in Mars' atmosphere today, about 10 parts per billion, if the measurements are correct. Mike Muma at NASA Goddard is one of the people that has measured this. That could be biogenic methane, but we really don't know. In fact, we're not entirely sure that the methane is there. However, we can't tell that. We can just barely tell that from Earth, I should say. If Muma's measurements are correct, he's doing high-resolution spectroscopy. Again, if you put this planet around another star, there's no way you would detect life there remotely. And just for completeness, the other place in our solar system where you might have subsurface life is Jupiter's moon Europa, which, as you know, has good evidence for a liquid ocean beneath the ice. And we know that because the Galileo spacecraft flew right by it, and Galileo had a magnetometer on it. And so when you fly a magnetometer, Jupiter has a very strong magnetic field, and if you fly, if you have a conductor that's passing through a magnetic field, it will generate a current. That's what happens when you walk through a metal detector in an airport security stop. And so Galileo detected currents within Europa's crust, and the only way that can really happen is if you have a liquid ocean that is salty, so it's got ions. And anyway, this was all anticipated by Arthur C. Clarke a long time ago. In 2010, all these worlds are yours except Europa, and attempt no landings there, right? In his book, there were these squid-like creatures living beneath the ice. There could be microbes living beneath the ice, and that's something else that NASA is interested in. The next big outer planet mission is not going to go back to Titan now. It's been pretty well decided it's going to be this, I think it's still called GEMO, the Jupiter Icy Moons Orbiter, and it's going to go and orbit Europa and I think Ganymede as well very closely, and they'll do careful, probably altimetry and gravity measurements and try to figure out how thick that ice is. If the ice is thin enough, like less than a kilometer or two, you may be able to actually melt your way through it and sample the ocean water beneath. So it's, as I said, the astrobiologists are really interested. But, it's irrelevant for planets or life, detecting life on planets around other stars. So we're back to, this is what I actually have worked on a lot for the last 20 or 30 years or more. I should say the way I got started on this was I read Carl Sagan's book in college, but then when I got out of graduate school, I went out to NASA Ames Research Center in the Bay Area, and I worked with Jim Pollack there, who was a very well-known planetary scientist. Jim was Carl Sagan's first graduate student, and he actually did a lot of the work on the greenhouse effect on Venus that Carl got a lot of credit for. And so I went out there to learn how to do runaway greenhouses and stuff from working with Jim. The problem that was interesting to us then, and is still interesting, is if you just think about the terrestrial planets, we won't count Mercury because it doesn't have an atmosphere, but there's Venus, Earth, and Mars. Lynn Margulis, who's the co-author on the Gaia Hypothesis, calls it the Goldilocks hypothesis. Earth is just right, Venus is too hot, and Mars is too cold. And the question is, why is that? Well, there's an obvious answer, and that's that Venus is too close to the sun, and Mars is too far away, and Earth is at just the right distance. But it turns out that there is more to the story than that, and that's the first part of my talk this afternoon. Let's think about the Earth's climate itself. It's not that easy to understand why Earth has remained habitable for the last 4.5 billion years. And that's because the sun has changed in luminosity over that time. This is a problem that was again pointed out by Carl Sagan and George Mullen about 40 years ago now. What's shown on this graph, this is one I made myself, time in billions of years before present, running from the formation of the solar system 4.5 billion years ago up to today. This solid yellow curve labeled S over S0 is solar luminosity relative to the present value. And as you can see, it starts out, the sun, we think, starts out about 70% as bright as today, and then it's been brightening more or less linearly with time. Why is that? Of course, it's not an observation. You can't even observe this by looking at other young stars. This is, it's basically impossible to tell based on what we know about modeling stars, at least their atmospheres. But it comes from models of stellar interiors. And we know that the sun is fusing hydrogen to helium in its core. As it does so, the core becomes denser, it contracts, it heats up, and that makes the fusion reactions go faster, because what you're trying to do in fusion is get two protons to stick together. They're both positively charged, and they repel each other electrostatically. But if they're moving faster, they have more of a chance of getting close enough for the strong force to act. So the astronomers, the astrophysicists, have known about this since the mid-1950s. I think Martin Schwarzschild and Fred Hoyle were two of the pioneers of this theory. They sort of neglected the consequences, though, because at the time when stellar evolution theory was being developed, the astronomers were much more interested in pre- and post-main sequence evolution. Before, as the sun is collapsing from a cloud into a star, it was originally 2 or 3 times as luminous as it is today, just because of the energy from gravitational collapse. Then on the main sequence, the sun's luminosity evolution is relatively slow. And then about 4 or 5 billion years from now, the sun will end its main sequence phase, and it'll go into the red giant stage. The luminosity increases by a factor of 1,000 to 10,000. And so that is, of course, much more spectacular, and that will really fry the Earth. I mean, it will certainly envelop Mercury, and might envelop Venus, and Earth will be fried. But, you know, Sagan was a planetary, he was an astronomer, but he was interested in planetary science. And what he did in this paper with George Mullen was, for the first time, point out that even this relatively slow main sequence evolution has really big implications for planetary climates. So let's look at the other curves here. T sub E is what we call the effective radiating temperature of the planet, which you get from planetary energy balance, just balancing the absorbed solar flux with the outgoing infrared flux, assuming that the planet is a black body, which it isn't really. But there's this little equation, which I don't think I have on this slide. Sigma TE to the fourth is S over 4 times 1 minus A. By the way, it's one of two equations in my book. My book is written at a semi-popular level, but that's one equation that is actually easy to derive and is very important for planetary climates. So as the sun brightens, T sub E increases by something like 20 degrees. T sub S, which is the upper dashed curve, is the surface temperature. And so that's a calculation here. And what I did was a calculation very similar to what Sagan and Mullen did. We just said, suppose the Earth's atmosphere was the same as today. Assume that the only two greenhouse gases are CO2 and water vapor. I'll talk more about greenhouse gases in a moment. But in this calculation, the CO2 level is held constant. Water vapor is allowed to change because water vapor acts as a feedback on climate. As the climate gets warmer, you get more water vapor in the atmosphere, and that gives you more greenhouse effect. So in this slide, that white area between the two curves represents the greenhouse effect of the atmosphere, which increases with time. Today, over on this side, the effective radiating temperature is about 255 Kelvin. The mean surface temperature is 288 Kelvin, or 15 degrees Celsius. And so the greenhouse effect is about 33 Kelvin. Back 4.5 billion years ago in this calculation, the T sub E drops by 20 degrees. T sub S drops by more than that. The greenhouse effect is only about 22 kelvins. And then if you look at the middle there, the mean surface temperature drops below the freezing point of water somewhere around 2 billion years ago, which is actually the same result that Sagan and Mullen got in their paper. Now, I'm in a geosciences department, and the geologists know that this is not what actually happened, because we have a geologic record that goes back to about 3.8 billion years. In fact, there's evidence now for liquid water back to 4.4 billion years. There are no rocks that old, but there are minerals within rocks, these zircons, that get recycled even after being subducted and going into the mantle. And the oldest interior parts of zircons are about 4.4 billion years old. And if you look at the oxygen isotopes in them, they're different from mantle values, which indicates that they had to interact with liquid water in such a way to fractionate the isotopes. There's a guy named John Valley at the University of Wisconsin that has made a big story of that. There's also evidence for surface water and for life back to about 3.5 billion years ago. So we know that the Earth was not frozen back during the first half of its history. In fact, there's not much evidence for glaciation. The early Earth, if anything, was warmer than the present Earth. And so that's the question, and you have to think about what the answer might be. Now, Sagan and Mullen, they suggested that it was the greenhouse effect that was bigger back in the past. They liked methane and ammonia, and that's because we also know, it's not part of my story today, but we know that oxygen levels were low on the early Earth prior to about 2.5 billion years ago. And so reduced gases that can react with oxygen, like methane and ammonia, could have been more abundant back then. Methane is a reasonably good greenhouse gas. Ammonia is a very good greenhouse gas, like water vapor. And so in Sagan and Mullen's model, they suggested that the Earth had somewhere between 10 and 100 ppms of ammonia. And that's what kept, early on, and that's what kept the surface temperature above freezing. Now, that theory was nice, but then the photochemists came along and they said, well, ammonia photolyzes. If you have ammonia is NH3, and if you hit that with solar ultraviolet light, you break you photodissociate it, you break it into nitrogen and hydrogen, the hydrogen escapes to space, and you're left with nitrogen, which forms N2, which of course is a stable molecule. And so anyway, at least up to the present, people haven't believed the ammonia hypothesis. Stay tuned on that, though. The story might change, and it's not something I can talk about today, but there are people who are trying to revive that hypothesis at the moment. So what else could it be if it's not methane and ammonia that we're keeping the early Earth warm? It could be CO2. And CO2 is one of the two main greenhouse gases today. So you have to say, well, what is it that controls the CO2 content of the Earth's atmosphere over long time scales? Of course, it's the carbon cycle, but it's not the part of the carbon cycle that you're probably familiar with. I mean, when I say carbon cycle, most people say, oh, okay, that's photosynthesis in one direction, CO2 plus H2O goes to CH2O, organic matter, plus oxygen, and that's reversed by respiration and decay, which goes back the other way. Well, that's the fast part of the carbon cycle, and that's what produces our oxygen and what we get taught in grade school, basically. There's also a slower part of the carbon cycle, which is called the inorganic carbon cycle, or sometimes the carbonate silicate cycle. And it's illustrated on this slide right here. If we start on the left, CO2 dissolves in rainwater, and that gives you a weak acid, carbonic acid, which of course you're all familiar with because that's the acid in soda pop. It's not very strong. You can drink it. But it's strong enough on long time scales to dissolve rocks on the continents. And it can dissolve both carbonate rocks, which dissolve pretty fast. It also dissolves silicate rocks, though. Most of the Earth's crust is made of silicates. And so that's represented here by this mineral reaction here, calcium silicate. That's the mineral wollastonite, which is actually a very simple calcium silicate mineral. That plus 2CO2 plus water gives you calcium ions. HCO3 minus is bicarbonate ion, and SiO2 is dissolved silica. And when gases, dissolved in rainwater react with rocks, the geochemists call that weathering. And this is silicate weathering because it's weathering of silicate rocks. All right, well, that takes CO2 out of the atmosphere, and the calcium and bicarbonate go into the ocean. And then in the surface ocean, organisms, some of the organisms there, some of the foraminifera, make shells out of calcium carbonate. And so actually Gaia has some validity here. Life is involved in this part of the cycle, even though it's what we call the inorganic carbon cycle. But these shells, calcium carbonate is CaCO3. When the organisms die, they fall down into the deep ocean, and most of the shells redissolve because the deep ocean is slightly more acidic than the surface ocean. But some of the carbonate is preserved on the seafloor, and it forms carbonate sediments down there. And actually the marine geochemists go out and in ships and they drill into those carbonate sediments and measure the oxygen isotopes, and that's actually how we get temperature and glacial interglacial fluctuations from that record. What we care about here is the carbon, though, and so there's carbon in those carbonates. The seafloor isn't just sitting there. It's spreading because of plate tectonics, and so it spreads away from the mid-ocean ridges, and at some plate margins, the oceanic plate is subducted. The carbonates are carried down. Some of them get scraped off, but some of it is carried down to depth, and of course, it heats up because of the geothermal gradient, and the pressure is higher. And because of those conditions, you get a process called carbonate metamorphism, where calcium carbonate recombines with SiO2, which by this time is the mineral quartz, and you reform calcium and magnesium silicates. Magnesium's not on this slide, but in doing so, you release CO2, and then that comes back to the surface through volcanism. So this is a slow part of the cycle. It's slow enough that it's slow on human timescales, so it's not going to save us from global warming. But it takes about 500,000 years to recycle all of the CO2 in the combined atmosphere-ocean system by this cycle. And that it's long by human standards, but if you're on the solar evolution timescale of billions of years, it's almost instantaneous, really. So now think about what would happen on the faint young sun problem if the Earth really was frozen over during the first half of its history, as I just showed you. the oceans would freeze. You wouldn't have any more evaporation and rainfall. You might get a little sublimation off the ice, and you get some snowfall to balance that. But you need liquid water to make silicate reactions go. Direct reactions between gases and rocks don't happen at any appreciable rate. You have to have water there to mediate the reactions. So if you did freeze over the Earth, then the weathering part of the cycle should drop off, but volcanism would continue. It may not look like it on this slide, but actually the mean residence time of seafloor is 60 million years, so there's lots of carbonate there. There's also CO2 coming out of hotspot volcanism like Hawaii and Mount Etna. So there's lots of volcanic CO2 sources. And so the idea then is that if the Earth gets too cold, you build up more CO2 until you get warm enough to unfreeze it. Now that, I used to think that was just a just so story. If you follow geology, you may know that there's evidence now for 2 or 3 snowball Earth episodes. Paul Hoffman at Harvard and Joe Kirschvink at Caltech have both argued that the Earth actually did freeze over 2 or 3 times in its history, most recently in the late Proterozoic, about 600 or 700 million years ago. I think that they're right about that, and the evidence for that is right on top of those glacial layers, you find thick layers of carbonate rocks, which we call cap carbonates. And Paul Hoffman's story is that what happened is that the Earth froze over, the cycle shut down, carbonate silicate cycle shut down, just as I explained. Lots of CO2 built up in the atmosphere. That melted off the ice caps, and then the Earth got really hot, and then you had an episode of very rapid weathering of carbonates and silicates, and you created a lot of carbonate rock and put that right on top of the glacial deposits. So anyway, I think that the story not only works in theory, but there's actually some evidence that it worked in practice. And also, just before I leave that, you don't have to freeze over the Earth before you get a feedback here, because if you make the climate a little colder, silicate weathering slows down. If you make the climate a little warmer, and of course if silicate weathering slows down, CO2 goes up. If you make the climate a little warmer, silicate weathering increases, CO2 goes down, and in both cases that counteracts the initial temperature perturbation. So, in fact, this is the whole basis for the theory. I'm going to get to the habitable zone around the sun. This is what makes the habitable zone wide, because if you push the Earth out towards Mars orbit, it would get colder, but think what happens is it gets colder, CO2 ought to build up in the atmosphere so you get more greenhouse effect. So instead of immediately freezing as you move the planet out towards Mars, it's got this built-in negative feedback that makes the habitable zone relatively wide. That's really the most important thing that I'll tell you, in my opinion. All right, well, why didn't that work for Mars? Mars is like Earth in some ways, and unlike Earth in other ways. It's certainly not habitable. You saw that from my previous slide. The mean surface temperature today is about minus 55 Celsius. But Mars is only it's half of Earth's diameter and about 1/10 of Earth's mass. And, if you've looked at pictures of Mars, we know it was volcanically active early in its history. It may or may not have had plate tectonics. It certainly had volcanoes, because you've got Olympus Mons there, which is the biggest volcano in the solar system, part of the Tharsis Bulge. And so, small objects cool off faster than large objects. And Mars cooled off when it was wet and maybe warm. That was, we think, during the first 700 or 800 million years of solar system history. After that time, Mars got too cool to recycle CO2, carbonates back into CO2. So its CO2 got trapped in carbonates. Mars' small size has another effect, and that's that it doesn't hold on to its atmosphere as strongly, and so it may have had a lot of atmosphere stripped off by the solar wind. In fact, there's isotopic evidence for that. You look at nitrogen isotope ratios, and Mars has lost more N14 than N15. That's because of stripping off, losing these nitrogen gases to space. So the point about that is it's not enough just to be at the right distance from the sun. Mars is, I didn't say this, but Mars we think is within the habitable zone today. If it was Earth-sized, it would probably be habitable. But because it can't recycle CO2, it's not habitable. And so size is an important part of the story. What about Venus? Venus is also obviously not habitable. You may know that if you know the history of this, back until about 1970 or so, people thought that Venus was actually, much cooler on its surface than it is today. I read a lot of science fiction growing up. I read Edgar Rice Burroughs novels. Anybody here read? So he wrote I read all his Tarzan novels and the Mars novels, and there were 4 Venus novels too. And so, Venus was populated by people and it had steamy oceans. People actually widely believed this in this country, back in the early part of the last century. And then, what came along is we got microwave measurements, and this was something that Carl Sagan actually did participate in. You can't see through the Venus clouds. That's a UV picture of Venus. In the visible, the clouds just look white. In the UV, you can see cloud features, but you can't see the surface. And the effective radiating temperature of Venus is only 200 Kelvin, so you have no idea what's going on underneath that. Microwaves, though, and also radar can penetrate right through that. And so once we started getting microwave measurements of Venus, the microwave temperature was really hot, and it's 730 Kelvin at the surface. And that was one of the things that made Carl famous, was his participation in understanding that Venus is hot. So what happened to Venus? Back in the 70s, there's a big argument as to whether Venus also has little or no water. The maximum amount of water in Venus's atmosphere is about 30 parts per million. I neglected to say it's got a 93 bar CO2 atmosphere with just a little bit of water vapor. And of course, you're way above the critical point for water, so there can be no liquid water on the surface. What happened to the water? Well, John Lewis from the University of Arizona used to argue that Venus formed dry and never had any water, and others argued that Venus formed with a lot of water but lost it through a runaway greenhouse effect. And that argument raged for a long time. It's pretty much over now for a couple reasons. One is that the D to H ratio in Venus's atmosphere, D is deuterium, right? So and H is just normal hydrogen. So an H atom is just a proton and an electron. Deuterium has a neutron as well. The D to H ratio in Venus's atmosphere is 150 times that in Earth's oceans. And this is something that's now it was measured by Pioneer Venus in the late 70s. It can now be done by ground-based spectroscopy. And, that's very, very hard to get if Venus never had any water. But if you had an ocean of water, or some fraction of an ocean of water, and if you lose it by photolysis and escape to space, the hydrogen escapes faster than the deuterium does, so you build up this deuterium enrichment. And so that's really what sort of ended the debate. But the models of planetary accretion, which you heard just a little bit about today, also predict this, because we now think that the water, for Earth, was not present in the material that condensed out at 1 AU. It actually had to come from the asteroid belt region or beyond. And so if you had these planetesimals mix around during accretion and stuff from farther out comes and hits the growing terrestrial planets, it's pretty hard to hit the Earth with stuff from the asteroid belt without also hitting Venus at the same time. And so the theoretical arguments actually back that up. So at any rate, the point is that Venus, we do think, had a runaway greenhouse where it lost its water, and that's basically because it was too close to the sun. So the simple story is right there. Once you lose the water, then there's no way of losing CO2. You can't form carbonates anymore. And Venus also had lots of volcanism, and so volcanoes put CO2 in the atmosphere, but in Venus' case, the atmosphere just serves as a big collector for CO2. And so I think we understand Venus's history reasonably well. Just while we're on Venus, here's a picture that is made, as I said, you can see through the clouds at radar wavelengths. This was made by the Magellan spacecraft back in the early 80s, I think it was, using this technique called synthetic aperture radar. And what you do there is you take images from different positions in the planet's orbit, and you effectively get an aperture that's the distance between these images, so you can make a picture using radar, and you're actually measuring radar reflectivity here. The brown areas are highly reflective areas. They're probably also high, so these are mountainous areas. The blue areas are the brown areas reflect radar in multiple directions, so they're rough. The blue areas are smoother. They're flatter and probably also low-lying. And these are all false color images here. They're colored in by the JPL artists, but they filled in the low areas there with blue as if it might have been filled with water at one time. the reason I put this up is that one of the arguments in rare earth has to do with plate tectonics. Ward and Brownlee are well aware of the importance of plate tectonics in the carbonate silicate cycle that I just described to you. But they argue that plate tectonics is unique to Earth. And their argument is pretty simple. They say Earth is one of 20 large planets and moons. They include the Jovian moons in the solar system. And the only body that exhibits plate tectonics is the Earth. Well, let's think about that argument. Mars, why doesn't Mars exhibit plate tectonics? Well, that's simple, right? It's too small and it cooled off. Venus, it's not, first of all, is there evidence for plate tectonics there? Anybody? I'm going to go ahead and then I'm going to come back to this because I've got a couple, it's probably not, but I've got a couple images of Earth. This is a topographic image of Earth, so it's not SAR radar, it's doing laser altimetry. And if you see this, you see this ridge running down the mid-Atlantic. That's the mid-Atlantic spreading ridge, which you can see very well in this diagram. That's where seafloor is being created. Here's a higher resolution image of Earth, which shows other things. You see mountain belts like the Himalayas there, where India is crashing into Asia. So you get these linear mountain chains that get formed by continental collisions. You get seamounts here running through the Indian Ocean. There's also some spreading ridges on there, which I'm less familiar with than the Mid-Atlantic ridge. Anyway, a good geophysicist can look at this immediately and see that there's evidence for plate tectonics on Earth, right? Now let's go back to Venus here. So what do you think? Is there evidence for plate tectonics or not? Yeah. Notice this. I didn't notice this till the other day. I was giving this talk. See that big ring right there? It's not. That's a big impact crater, right? That's not plate tectonics. You see, what are probably high areas and low areas. There actually are altimeter data for Venus too, because you can do radar altimetry. It just doesn't make as nice of a plot. On Earth, you have a bimodal elevation distribution. 2/3 of the Earth is very low sea level, and then the continents are average a kilometer above sea level. And these features that I just pointed out. Anyway, the people that have looked at these images conclude that there is, it's very clear that Venus does not have plate tectonics. You don't see the same types of features that you do on Earth. So why is that? Venus it's not quite the same size as Earth. It's about 80% of Earth's mass, but that should be big enough that it has internal heat. Why doesn't Venus have plate tectonics, but Earth does? Anybody want to hazard a guess on that? What? Water, yeah. So that's what many of us think. At least I'm not a geophysicist, but water is very important for plate tectonics. And in particular, it's not just the crust that's sliding around, but it's the lithospheric plates that are about 150 kilometers thick. They're sliding around on the semi-molten asthenosphere, and the upper part of the mantle is semi-molten because water depresses the melting point there. And so it basically acts as a lubricant. And then water also cools the plates where they come out at the mid-ocean ridges. There are these hydrothermal vents. So it's cooling the plates and stiffening them as they spread out. And so, the analogy I think of is pretty simple. Water is to plate tectonics as oil is to an engine. And if you take out the water, it's not well lubricated. It seizes up. And in fact, there's other things. I don't want to get stuck on Venus, but you can look. The entire surface has randomly distributed craters, which means that the entire surface has roughly the same age between 500 million and 1 billion years. And we think that what happens is there is no plate tectonics for a long time, no volcanism, and the geothermal heat builds up on the interior. Eventually you get a planet-wide melting event. You resurface the whole planet, but then that lets the heat out, and then it seizes up again. So the heat does get out, but it doesn't get out in a smooth way like it does on the Earth, right? So anyway, what's the point of that? Plate tectonics is unique to the Earth, but the reason Venus would have it if it had its water, and the reason Venus doesn't have plate tectonics, in my opinion, is because it's too close to the sun. It's the same problem with its lack of water because they're directly related. How am I doing on time? 10 minutes, okay. So I will go faster on this. This leads to this concept of the habitable zone, defined as the region around a star where liquid water can remain stable on the surface. The other thing that got me interested in graduate school was there were two papers that came out in the late 1970s by Michael Hart, who was a planetary scientist at NASA Goddard. And one was on the habitable zone around our sun, and the other was on the habitable zone around other stars. His conclusion for the sun was that the habitable zone was very narrow. It only went from 0.95 AU out to 1.01 AU. And then for other stars, they were all narrower or non-existent. So Hart concluded that Earth might be the only habitable planet in the galaxy. Well, what's wrong with that? His model didn't have that CO2 feedback in it. And so, if you push the Earth out to 1.01 AU, where his planets froze over, the solar flux goes down by 2%, according to the inverse square law. But we just saw that the solar flux was 30% lower early in the Earth's history, and it didn't freeze the Earth over, at least not for very long. So anyway, we now think, at least I think, that the habitable zone is wide because of these feedbacks in the carbonate silicate cycle. This is a diagram that was made by some colleagues over in Europe, which is, I made this picture originally, but they've made a much prettier one than I can, so I'll show this one. This is distance in astronomical units of the planets from the star, and on the vertical scale is the mass of the star relative to the mass of the sun. These, of course, are they've got 9 planets in the solar system here, so we should probably take Pluto off. But the habitable zone is the relatively wide blue area going through there. And of course, it's for the brighter blue stars, the habitable zone has to be farther out, and for the dimmer red stars, the habitable zone is further in. Earth is somewhere comfortably in the middle. Mars, in this diagram, looks like it's just on the outside. That's because this is for zero-age main sequence, when the sun was 30% less bright. So today, the habitable zone moves out with time, and that was actually something I liked about Hart's papers. He defined the continuously habitable zone, which is the region that remains habitable for some time period as the star brightens. So anyway, Venus is inside the inner edge. Now, let me show this. This is the one diagram I used to show that has the same diagram, but it's got one other thing on it. And I wanted to make this point while we're here. This dashed line there is the tidal locking radius of the star. So if the planet is too close to the star, then its rotation will be captured. And, the moon's rotation around the Earth is captured, right? Because if you look at the moon, we always see the front side of the moon. It's because it's within the Earth's tidal locking radius. Well, for late-type stars, the red dwarfs, the late K stars and the M stars, the habitable zone is within the tidal locking radius of the star. And so that means that these planets around, there might be Earth-sized planets around M stars, but they're most likely going to have a permanently sunlit side and a permanently night side. And that may or may not pose, doesn't necessarily mean that they're uninhabitable. If you can transport enough heat around to the night side, then things could be okay. But if you don't transport enough heat to the night side, then you'll freeze the atmosphere and the oceans out on the night side, and no part of the planet might be habitable. Right? Okay, now I'm almost out of time, so I just want to... Part 2, you've heard parts of this. Indirect detection methods, Alan covered nicely in his lecture. What we're really interested in is direct imaging. Where you separate out the light from the star and just look at the light from the planet and then get a spectrum. Like you see, you get a crude spectrum in a rainbow because the water vapor droplets are acting like a prism. Alan showed you this picture. This is the basic story of if you look at the Earth around the sun. How many minutes have I got left here?
5.
About 5. Okay, so I can do part of this. If you look at, this is now in wavelength, this is microns. The visible has been between 0.4 and 0.7 microns. Right over here, that blue area is where TPF coronagraph would operate. That's the light from the star. This is from a distance of 10 parsecs or 30 light years. This is the light from the planet. And here, if you notice, the Earth's radiation curve parallels that of the sun. That's because you're looking at reflected light from the star, right? And then out here, as Alan said, that's the Earth's own emitted thermal infrared radiation. So the question is, which one of those do you want to look at? Initially, NASA thought we should look out in the infrared because the planet is relatively brighter compared to the star. It's only 10 to the 7th times dimmer than the Earth is only 10 to the 7th times dimmer than the Sun in the infrared. It's 10 to the 10th times dimmer in the visible. Now the disadvantage, though, is which also Alan mentioned briefly, is that the spatial resolution that you get from a telescope. There's a theoretical diffraction limit there. Theta, the angle, minimum angle that you can resolve is equal to lambda over d, where lambda is the wavelength of light and d is the diameter of your telescope. So if you're trying to find this planet very close to the star, and if you're in the visible right here, say working at 0.5 microns, you can get by with about an 8-meter telescope. And that was the one that Alan described, the TPFC thing, the 3.5 by 8-meter telescope. But if you go out to the infrared out here at, say, 10 microns, then you need, instead of an 8-meter telescope, you need an 80-meter telescope. And then you need to do interferometry, as Alan described. Now, I skipped the pictures here because you saw this. The interferometer is now this EMMA X-wing array. And I've got a virus here, don't I? So get rid of my virus. And if you were in the infrared and we're looking at Venus, Earth, and Mars, if you could get these spectra, this is now in the thermal infrared. For Mars and Venus, they have CO2-dominated atmospheres. And what you see is this very strong 15-micron band of CO2. That's the one that contributes to global warming on the Earth. On the Earth, you see that 15-micron CO2 band, but you also see this is a water band here, and that's another water band. And right here, right at 9.6 microns, there's a very strong ozone band. And ozone comes from photosynthesis. Well, ozone comes from oxygen. Oxygen comes from photosynthesis. So this might be evidence for life if you saw that ozone band. And then I'll just show you one more thing. This is that TPFC coronagraph, the visible telescope. There's another version of that that's being considered right now. Instead of trying to block out the starlight internally with a coronagraph, you may be able to fly an occulting disk out in front of the telescope. So this is Webb Cash's idea at University of Colorado. You've got about a 4-meter telescope, and you fly this 50 to 70 meter diameter occulter, but about 50,000 kilometers away from the spacecraft, and you use that to block out the light of the star. Turns out that works really well on paper because you get rid of all the diffracted light. And I'll finish here. This is what you could get with a spectrum of the Earth with an occulter or a coronagraph. This top curve there, the black, is the Earth's spectrum in the visible. Now this is in angstroms, so 7,000 angstroms is 700 nanometers. The visible is down here, and this is the near infrared. The way this spectrum was gotten, by the way, is it's called Earthshine data. It was hard to get what you want is a 1-pixel resolution image of the Earth, and you can't get that from a near-Earth orbiting spacecraft because the Earth is too big in your picture. So for a while, the exoplanet guys were thinking of sending a satellite out to the Earth-Sun L1 point and looking back. It was called Triana for a while. Al Gore wanted to do this for other reasons. That was going to be a $30 million instrument. And then this group at University of Arizona, Nick Wolf and Wes Traub was part of this, figured out you can do the same thing by, you look at the dark side of the moon. And if you've ever looked at the dark side of the moon on a clear night, you can see it a little bit, right? It's glowing, and why is that? It's because the sunlight's hitting the Earth, bouncing off the Earth, hitting the moon, and then being reflected back at you. And so the way that they do this then is you measure a spectrum of the dark side of the moon, measure a spectrum of the bright side of the moon, subtract out the bright side from the dark side. That subtracts out the moon spectrum, and you're left with the Earth spectrum. And so instead of spending $30 million to go to L1, they did this from KITP and in a couple of nights and got this really wonderful disk integrated spectrum of the Earth. Right here at, there's some this is a model fit. There's some water bands down here in the near IR. There's an ozone band down here in the visible, and there's a very strong oxygen band, O2 band, at 0.76 microns. So again, it's the same story. That would be pretty good evidence for life if you were to see that, because most of Earth's oxygen comes from photosynthesis. So I'll quit there. There's more slides in the talk, but I think it'd be better to open up for questions. Thanks.
All right, lots of questions. Sure, let's start here.
You mentioned that about the oceans on Earth was because of the capturing of the asteroids, the icy asteroids as they were hitting the Earth. The water from them was captured by Earth. Is it a new theory, or was it? Is the older version of the theories died out? Or?
Oh, it's not that new of a theory. So in John Lewis's model, it was called the equilibrium condensation model. He thought that the Earth got its model from hydrated. So he was doing thermodynamic equilibrium. He had a model of the solar nebula that had a pressure-temperature profile along the mid-plane, and he thought that the way that the Earth got its water was from hydrated silicates, which he thought would form at 1 AU, but they wouldn't form at 0.7 AU where Venus is. And that really doesn't work because, thermodynamically it works, but kinetically it doesn't work. And so even way back around by 1980, a lot of people had realized that, and they knew that the water had to be coming from beyond 1 AU. So I would say that the idea is new, but it's new 30 years ago. And the debate more recently has been whether the water comes from asteroids or from comets, which come from farther out. That's also, the D to H ratio bears on that, because the D to H ratio has been measured now for 3 comets, Halley, Hyakutake, and Hale-Bopp. And for all 3 comets, they have D to H that's twice that of Earth's oceans. So see, that would indicate that you can't form the Earth's oceans from comets, because if you start out with a D to H ratio that's twice too high, then if you lose hydrogen, you just make that worse, because you lose the H faster than the D. And so if those 3 comets are representative of other comets, you can't use the comets as the major source of water. You have to use asteroids.
You stressed the importance of the carbonate silicate model. I'm back here, if you're wondering where I'm at.
Sorry.
You stressed the importance of the carbonate silicate cycle. Doesn't that assume life? And what would be different if you had a liquid ocean on a planet with no life? Would you still have a carbonate silicate cycle?
So that's a very good question. Is Lovelock really right there? The calcium carbonate today on Earth is precipitated mostly by organisms. But if you go measure the solubility of calcium carbonate in seawater, or measure the concentrations of calcium and carbonate, you find out that the surface ocean is already supersaturated by a factor of between 2 and 5. But the carbonate formation is kinetically inhibited, and it's the organisms take advantage of this and just catalyze the precipitation. If you didn't have the organisms there, then you just simply would build up a slightly higher supersaturation, and that carbonate would come out abiotically. In fact, it probably comes out that way in these things called whitings that occur occasionally today. So that the other place where life affects the cycle is life affects silicate weathering. And so this turns out that if you measure the CO2 concentration in air spaces down in the pores in soil, it's 20 or 30 times higher than it is in the atmosphere. And that's because you have vascular plants like trees that are creating root systems. So they're putting organic carbon into the soil in their roots, and then you get this. Plants respire just like animals do. So you get root respiration, and you also get bacteria down there that create humic acids, which are stronger than carbonic acid. And so bacteria and life probably accelerate silicate weathering. Again, so life has an effect on that cycle, but you would still get the cycle operating without life. So the Earth is partly Gaian.
The Mars used to have a magnetic field just like the Earth, and that, of course, the Mars does not have the same magnetic field that it used to have. So I know the scientists are interested in looking at what made that magnetic field change for Mars, so that they can understand if the same thing will happen for Earth.
You may know more about this than I do, but I think the evidence is, the jury is out as to whether Mars had a magnetic field. You know, there were these stripes that were reported in Science several years back that some people thought looked like seafloor. The way we know the seafloor is spreading because of the magnetic stripes parallel to the ridge axes. And there are 4 big magnetic stripes in Mars' northern hemisphere, which were interpreted by the observers initially as being possible evidence of seafloor spreading, but I think that has gone by the by. And so I don't think we know if Mars had a magnetic field at one time.
Yeah, this is sort of a red herring, but I want to just ask you about it. Recently, a couple of years ago, there's something in the popular press about our going around the galaxy and a changing background of cosmic ray flux. Also a solar minimum that we head into, subsequently changing the amount of cloud seeding, and that changing basically the amount of temperature on the Earth. I'm just wondering if anything has crossed your path and if you have any opinion on it.
Well, that is Nir Shaviv and Jan Weiser, I think, who they don't believe in global warming, so they're trying to prove that CO2 doesn't affect temperature. There are these climate cycles during the Phanerozoic, the last 500 or 600 million years, which most of us think are being driven by variations in CO2. But Shaviv and Weiser were trying to tie that through passage of the Earth through the spiral arms of the galaxy, which I think there's a couple different papers here, so I may be confusing papers. And there's really very little evidence. This is the reason I think of that one is that they also, this has been picked up on by others as another argument for why Earth is unique. Just one moment. There's an argument that that I think is also Shaviv is involved in, that the Earth is right at the co-rotation point in the galaxy where it stays out of spiral arms because it's orbiting the galaxy at the same rate that the spiral arms. And he would say that if you went into a spiral arm, the odds of getting a nearby supernova would go up. So the sun has to be just the right distance from the center of the galaxy to avoid getting into spiral arms. But I think that one hasn't held up because the rotation rates are not known that well.
We're going to take one more in the front here and then in the back.
How much credit do you give to the formation of the moon making the Earth more habitable?
Oh, so that's another argument that Peter Ward and Don Brownlee make a big deal of in Rare Earth. And that's, if you just take the Earth-Moon system today and take the Moon away without doing anything else, then the Earth's obliquity goes chaotic. So the obliquity is the tilt of the spin axis relative to the orbital plane. Today it's 23.5 degrees, and it varies from 22 to 24.5 degrees on a 41,000-year period. If you take away the Moon, then basically the Earth's precession rate is slower, and it gets into resonance with some of the orbital forcings from the outer planets. And so the Earth's obliquity would go chaotic. But if the Earth was rotating faster than 12 hours, then its obliquity would be stable again because that speeds up the precession rate. And so you have to ask, how fast would the Earth be rotating back in the past if it didn't have a moon? Well, what the moon is doing is it's slowing down the Earth's rotation rate. So we think that the Earth was originally rotating at about a 4 to 5 hour spin period, but this is a triple-edged sword. Why was the Earth rotating so fast back in its early history? It's because of the moon-forming impact, which spun it up. So the question is, if you didn't have that impact, what would be the rotation rate of the Earth? Would it be faster than 12 hours or slower than 12 hours? I would argue that you just don't know that. And
so there is, back here, you made an interesting argument about the potential for G stars having greater potential capacity for habitable.
Where's the question?
For G stars having greater capacity for habitable life. If you were to do a density curve, or excuse me, if you were to do just take a look at the distribution of G stars throughout the galaxy, first off, would it be similar throughout the galaxy? And secondly, what kind of percentage of stars in our galaxy would you estimate would be actually G stars?
Is Deborah still here? Deborah, do you want to take a crack? Deborah knows the stars.
Well, no, I think that the stars are distributed uniformly, so I think you expect as many G stars in the rest of the galaxy as you have here. And since 70% of the stars are M dwarfs, something like 10% of the stars, 12%, I don't know, are probably in the G solar type stars, the late F, early G, mid G type stars.
We don't just think it's G stars. We think it's F, G, and early K stars are the best candidates for having Earth-like planets. If you get earlier than F0, an F0 star has a 2 billion, the main sequence lifetimes get short. So an F0 star has a 2 billion year main sequence lifetime compared to 10 billion years for the Sun. Once you get past about K5, then you get the planets, the habitable zone moves inside that tidal locking radius. So you're going from short lifetimes and also high UV around the early type stars and tidal locking possibly around the late type stars.
We know that there are stars and star systems. Oh, thanks. Stars and star systems with very different ratios of carbon to silicon, oxygen to nitrogen. This may be crazy, maybe you touched on it, but have people thought about what that might do to the habitability zone, or is it that the exact ratio of carbon and silicon does not have much of an effect on the carbonate-silicate cycle, like limiting factors?
Well, I think it would have a big effect if there are these carbon stars where the C to O, in our Sun, oxygen is more abundant than carbon by a factor of 2, is it? As I said, I'm not a very good astronomer. But that's important because carbon likes to bond with oxygen to form CO, and if you have more oxygen than carbon, as you do in our solar system, then you form that CO and there's a lot of oxygen left to form water. If you had more carbon than oxygen, then you would bond the oxygen as CO and you wouldn't get water. But carbon stars, the question is, if you have a carbon star, do you also have carbon planets? And I think the answer to that is maybe no, but who actually knows that? I don't know that much about carbon stars.
I'm old anyway, but
Mark Kuchner has told this story, but then I was told that you shouldn't really worry about it. That carbon stars are they're rare to begin with, and so most stars are like the Sun in that they have more oxygen than carbon, and that's just because during nucleosynthesis you're more likely to make oxygen than you are carbon.
Thank you.
All right, one more question before break.
This has to do with the D to H ratio of water. Or you find on Venus, you said that the water went away very early. Did that water originally come also from asteroids? And the other question is, was it a single asteroid impact that brought all the water to the Earth? Is that what or is it multiple asteroids striking the Earth? Or I'm just really curious about that.
These are good questions, actually. It's probably multiple asteroids, but in the modeling that has been done, one of the guys who's done a lot of this is Sean Raymond, who Sean's probably not here today, but he'll be here during this conference that we're having this coming week, and he's tried to model exactly that. And what he has shown, actually, is that if you get one large water-rich planetesimal coming from the asteroid belt region, that's enough to supply all of Earth's oceans. So these planetesimals coming in, they're not 10-kilometer sized things. They're up to, well, the moon forming impact, that was a Mars-sized body. That was at least a tenth. In fact, the best models say that was 2/10 of an Earth mass, the object that hit. So you get one of these large bodies coming in from the asteroid belt region, you can bring in fact, the danger is, I would say danger in quotes, is that you can bring in a lot more water than the Earth has. And so the astronomers are now interested in what they call water worlds, because in some of Sean Raymond's models, you get planets that are like the Earth, but they have 100 times as much water. And so the oceans, instead of being 4 kilometers deep, would be 400 kilometers deep. And, we think we may see these things, and that's something that to look out for in the future.
All right. With that, we have a nice long break. We're coming back here at 3:15. So let's thank Jim again.